Hi everybody, this is Dr. Bricker here with an introduction for our photoelectric effect lab. So I've logged into Pivot Interactives and I'm going to choose the photoelectric effect lab. You can see what it looks like here. And I've logged in as Testerson again. So the activity has two parts, as it says here. First, we'll explore how the potential and current in a phototube are affected by the intensity of light shining on the tube. And then next we'll apply the principle of the photoelectric effect using this equation that you've seen in class. Maximum kinetic energy is equal to H times F minus the work function. So there's a little bit of different notation. This phi here is the work function. We use E sub 0 in the textbook, but this means work function when you see that. So we'll be able to actually calculate the work function of an unknown cathode, and we'll also be able to come up with Planck's constant using the photoelectric effect. So pretty cool stuff, actually. So so here's the video. Maybe I'll just show you what the video looks like before we get started. And I'll hit play. So there's going to be a laser hitting the phototube. A little bit loud, sorry about that. And you immediately see, I paused it, that you have some current that's produced. So the idea with the photoelectric effect, you have light that has enough energy, or high enough frequency, small enough wavelength. It's incident on a piece of metal. Electrons are freed and they're able then to drift across the tube. And we can set up a small voltage to kind of guide the electrons across. Okay, good. So you see there's a whole bunch of current here, too much for this to even measure. And right here what you're seeing is there's a really big potential setup. So really electrons are being freed, they're being guided across the tube. This voltage that you see here is the voltage that's either being used to guide the electrons across or being used to stop the current from flowing at all. So this says adjusting the stopping potential right here. So this is the stopping potential. So refer back to chapter 28. This is the voltage that's used to completely stop the current from flowing. Okay, so the electrons want to drift across the phototube. This voltage is stopping them from doing that. Okay. And you see zero current. Okay, now they're turning down the stopping potential. Now you actually get some current flowing across. So from the stopping potential, we will actually be able to use that in conjunction with the frequency of the laser to figure out the work function of the metal and also Planck's constant. That's the last part of the lab. But that's the idea here. Okay, very good. Back to this. So at the heart of this apparatus is the phototube, glass bulb, which is evacuated, nearly all the gas is pumped out, with a curved upright metal surface, that's the photocathode, and a vertical wire electrode, that's the anode. So here's a nice picture of it. Okay, so light's going to be shining on the photocathode. If the frequency is high enough, you'll get some electrons that are liberated and they drift across, and a small potential is set up to have that happen. Now if we want it to completely stop working, we stop drifting across, that's where we set up the stopping potential, as you saw in the video. Okay, so there's a couple of questions about that. When light shines on the photocathode, electrons can be liberated from the surface and can accumulate on the anode. Okay, so they're freed here, and with a small potential setup you can get them all to drift across to the anode. Okay, based on this, what electric charge would you expect to accumulate on the photocathode and anode when electrons are emitted? So think about that. You're freeing electrons from one, they're drifting over to the other. So I'll leave that up to you to answer it. So you have 3 submissions to do that. So you should be able to get that one. A couple of points there. Next, let's look at some experiments we can conduct with the phototube. So we'll go to the next part here. How does intensity affect light? Okay, so let me just again play the video and then we can talk about some of the questions. And you can change things here. Right now what you have is a voltage. You can click this and instead have a current being measured, you can change the kind of laser you have. This is a higher energy laser. This is lower energy. I'll just leave it like it is now. Whoops. There we go. And let me go back. Okay, so same photo tube, different laser though. So if you notice, you can kind of see what the voltage is here. Here is where the intensity is not as great, and you have to watch the video, and they're going to turn up the intensity, which means the light gets brighter and brighter and brighter. Okay? So you see that the voltage is not changing here. This is just the voltage to direct the electrons across. Let me actually measure the current though. Same laser, and we load this one. Okay, and then we'll hit play again. Now the intensity you get from it's not as bright, and then it gets brighter and brighter and brighter. We can see what happens to the current. So I is for current. You can kind of see it's something like right in here. It's hard to see because it's dark. Oh, the intensity went up. You see there's more current. So basically there's more of these high energy photons coming in. So more electrons are liberated. You have a higher amount of current. Oh, even greater. So the current is what's really measuring the liberated electrons. The voltmeter is just used to set up that voltage to direct the electrons across. And if we flipped it around, we could actually stop that from happening. Okay, so use the video. Does the intensity affect the amount of current that flows through the phototube? So I mean, you kind of already just saw what happens. But play around with a couple of them, and you can answer that appropriately. Does the intensity of the light affect the voltage across the phototube? So the voltage across the phototube is not affected by that. The voltage across the phototube is what you set up to direct electrons across, or to completely stop them from coming across. Okay, so it's just like the phototube idea in the book. And then using the photoelectric effect. So here's the equation that you saw from chapter 28. Maximum kinetic energy is hf minus the wavelength. So h is Planck's constant. This is the work function. So the maximum kinetic energy, whatever's left over after overcoming the work function, electrons get some kinetic energy. That's what this represents. H is Planck's constant. F is the frequency of the incident photon. Now, in the video, they give you the wavelength, but there's a nice relationship between frequency and wavelength. You'll have to solve for that. So remember, the speed of light is equal to the frequency times the wavelength. So if you want to get the frequency, do one step of algebra. Speed of light divided by the wavelength will give you the frequency. Now just be careful. These wavelengths are given in nanometers. Make sure that you put times 10 to the minus ninth when you do the math for that. H is Planck's constant. F is the frequency, and phi here is the work function. Okay, good. So you'll see a person adjust the variable resistor on the right side of the circuit. This will create a voltage from the power source on the right side of the diagram. As the voltage increases, the anode becomes more negatively charged. So what you're doing then is keeping electrons from drifting across. And when there's no more current, that's when you've kept all of them from coming across. That's the stopping potential. So as the power supply stopping voltage is increased, what happens to the flow of electrons from the surface? So I kind of already gave this one away too. So let's watch it and then we'll answer it actually. I said it in words, but let's see what it actually looks like in the video. Okay, so this is, we'll just leave this at medium intensity. Here's the wavelength. There's 5 different ones actually. We'll just leave it at 532, and I'll just put load. I think it's already loaded. Okay, and let's see what happens. Okay, good. So you see a whole bunch of current flowing because there is no stopping potential. This is the stopping potential. Now, as the stopping potential is increasing, we should see the current drop off. Okay, stopping potential 0.4 volts. the current is down to 3.5. What we want to do is make the current go down to 0 and read that stopping potential. Now, if this class were in person, we actually do this with, I think, 4 different frequencies of light. We set this up, we increase the stopping potential till we get no current. Okay, current's going down. We want to get to the point where there's 0 current. A little bit more. And I'll pause it there. That looks pretty good. So you can read the stopping potential here then. Whatever this turns out to be, you can see it better than me. 0.87 or so. Looks like it's between 0.86 and 0.88. So about 0.87. Keep the intensity the same, and then you can change the wavelength, figure out what that stopping potential is. And we're going to use all this information to come up with, again, Planck's constant and the work function. Okay, so right now in this picture, we've stopped all the electrons from coming across. They had kinetic energy. We've turned that kinetic energy into electrical potential energy. Okay, so they don't have enough kinetic energy to overcome that. Okay, and now here's the part where you're going to get some data. So we want to use 5 wavelengths, so you're going to have to build this table yourself. Name these things whatever you want to. So you're going to have a column for wavelength, and whatever you want to call that wavelength. Maybe it's hard to type the symbol lambda. Whatever you want to call the wavelength. Units. Right now it's set up for nanometers. So 532 nanometers. And then what you want to measure is the stopping potential. So you have to have another column over here. Stopping potential, units would be volts. Okay. Now you're going to have a few more columns, so you'll have to add those. I think if you just click here, insert column to the right, we want to have a column of frequency. So if you have the wavelength, you can calculate the frequency. Let's do another column. Insert column to the right. You want to have another column of kinetic energy. So what is the kinetic energy equal to? It's equal to the charge. It's an electron. So this column would be the kinetic energy. That's the charge, 1.6 to the minus 19th coulomb, and we just want the magnitude of it. 1.6 to the minus 19th coulombs here times the voltage, the V stop. So Q times V stop, that is the kinetic energy. So you want to have a kinetic energy column. Okay, so what are we going to use all these things for? You're going to build a graph down here once you've set this thing up. So you have to put you've got to name it, put the units and the variable. And then remember, these graphs, things will appear here that you're able to actually graph. So let's take a look at how this is going to work out. Okay, so here's the equation that we have. Kinetic energy max, HF minus the work function. Okay, so you're going to have 5 different frequencies. You'll have to, again, take the wavelength and convert it into frequency. This is how you do that again. Speed of light is the frequency times the wavelength. So the speed of light divided by the wavelength is the frequency. Now just be careful. This is probably going to be, whatever it is times 10 to the minus 9th. The speed of light, 3 times 10 to the 8th, meters per second. So the frequency will come out in hertz, which is a 1 over a second. So don't be surprised if that's a really big number. You'll have to put it in as something probably like times 10 to the 14th power or something like that. Okay, so we're going to create a graph of kinetic energy over frequency. Okay, so why are we doing that? We've done this again. We did it last week, I believe, or the week before, many different times. This is in this form. Y is equal to mx plus b. Okay, so the y in this lab is the kinetic energy. The x is the frequency. So this is the intercept. So if you want to get the work function, that's what the intercept is. Okay, so once you graph this, you should get a nice line. These points are something probably like over here. I don't want to give it away too much. Yeah, I don't want to draw the line. Anyway, you'll get a line. It'll cross the y-axis, and the intercept then is the work function. Okay, so that will be in joules. There's a question asking you about, how does that compare to some number in electron volts? So if you get the intercept, it's going to be in joules, right? Because the unit here is going to be joules. You'll have to convert that to electron volts if you want to compare it to something that's in electron volts. Now the slope, it's whatever comes in front of the x variable. The x variable is the frequency, so the slope is actually Planck's constant. Okay, so you can kind of read those from the graph actually. So let's go back to the actual lab. By the way, you'll get a value for Planck's constant here, and you can compare that to the known value of Planck's constant. It should be relatively close. Okay, and then the last couple of questions deal with this whole idea, what does the y-intercept represent? I've kind of already given that one away too. How does it compare to 1.8 electron volts? So whatever you get for the work function, you have to convert it to electron volts to compare it. So by compare it doesn't mean like it's almost the same. It means how does it compare? Find the percent difference. That'll give you a sort of a quantitative way of looking at it. Okay, very good. And then same idea with the slope. What does the slope represent? And so that's the one that's Planck's constant. How does it compare to the known value of Planck's constant? Again, don't just say, well, it's close. Quantify it. What's the percent difference on that? Okay, have some fun with it. I think you're going to like it, and I'll talk to you soon. Bye-bye.